Oh, so welcome everybody, and special thanks to Rob, who's going to give us a talk. I'll let him do the introduction. Over to you, Rob.
Uh, yes, okay. Okay, so uh,
There will be various pings from time to time.
sure, sure.
Uh,
So those of you who know me probably know I've never been able to actually prepare a talk on paper before, almost ever. I mean, a few times I did. So I was going to write out some stuff on this tablet, this on my iPad, but it didn't happen. And so, but I think it's in my head. So I decided that I should not assume that all of you know what a trisection of a four manifold is, that I should start at the beginning. Uh, I know that some of you have at least maybe heard a talk or glanced at it or something, but probably not everybody. So what's a trisection? Well, a trisection, so we're going to be talking about, let's see, I don't want something that thick. There. Trisection of a four manifold. And our four manifolds, is this working okay?
Looks great, Rob.
yeah.
Okay. All right. So trisection of X4. And X4, I'm not going to write it all out, but it should be smooth, oriented, compact, closed, one of those four manifolds. And so a trisection of X4 is like a bisection of a three manifold M3, otherwise known as, which is equal to a Heegard splitting. So it's just you get a Heegard you get a Heegard splitting by taking a map of M to the reals. Take a nice Morse function, and then you have on the three manifold. You then have a critical point of index 0, some critical points of index 1, some critical points of index 2, and you can have one of it index 3, and then you just cut it in half. This is the Heegard surface. And you have a handle body below and one above. And a handle body is just equal to a connect sum of, S1 cross E2s. Connect sum of a bunch of those. In other words, you fill in a surface. You fill in the Heegard surface with that. So that's what a Heegard splitting is in dimension 3, and you could call it a bisection because it has two halves. Okay, now for a trisection of a four manifold, well, this all began with a Morse function, well, a Morse 2 function. So here we go from X4, and we map it to the plane, which you could think of as the complex numbers sometimes. So this is a Morse 2 function. All that means is that it's a map to the 2 dimensions rather than 1 dimension. And the origins of this came from elliptic surfaces, or came from the complex or the algebraic geometry world, where you had things like the K3 surface or complex surfaces, and you map them down to the 2 sphere. And so that's a map from a four manifold to the plane. And those maps were studied, and there were singularities. And sometimes you had a non-singular fiber, which was just a 2 manifold lying over a point in the plane. And sometimes that 2 manifold had singularities. So you got pictures like this is the 2 sphere down here, same as R2 for our purposes. And then above it, over a point, suddenly this became an eraser. So over a point, you might have a surface. You might have a surface over a point, or you might have more singular things. And the singular things, for example, there's something called a cusp, And this was a two-sphere. This is a two-sphere. And around this point, that point means that you see the cone on the trefoil knot. So the cone point is the point, and then the stuff going into the cone point represents the cone on the trefoil knot, and then the trefoil knot bounds a sphere. Sorry, bounds a in this case, it just bounds a sphere. It's a circle, so it bounds a disk. So that was the picture that got generalized, that we want to generalize to a Morse 2 function, where we sort of lose the complex structure. But down below, we have, okay. So next then is, fortunately, I can't keep this blackboard. And, so what we see, so now I'm going to draw a picture of the circle. This is a circle in the plane. And inside, this is you're to think of this as like the two-sphere before. And so over a point, so over the center point, you're going to see a surface of genus G. So we're starting to construct a four manifold here. And so we've got a disk, and we've got then over the center point, we have a two-sphere, and over a neighborhood, you just have the two-sphere across a disk. And then as you go out, in various directions. So as we go out in this direction, that's a line in the plane. So over that line, you're going to see a three manifold. And the boundary of that three manifold is the surface of genus G. And out at the end point is just a point. And you want to if you think of a Morse function on that three manifold, well, that three manifold is going to be, as before, a connect sum of S1 cross B2. It's going to be a handle body. So this is a handle body. So this is a very simple thing. Surface, body, the handle body, and this is sort of the minimum. If you had a Morse function, this point's a minimum. And then you have more of these. You have another one. This is where the tri comes from. You have a blue one. Same features. This is again a handle body. Again, surface of genus G. And then one more, which I'll call green. Same thing here, another handle body. And this is giving you, this is now the four manifold lies over this, and all I've told you about is the surface over the center point, and then handle bodies over those three lines. And now how do you fill it in to get an actual four-dimensional thing? This is kind of like a spine that I've drawn so far. Well, you fill it in by putting in here, we have, again, a handle body, but it's a four-dimensional handle body. So over this guy here, we have a 4D handle body, which is a connect sum of copies of, it's going to be K copies. This was G copies. It's going to be K copies of S1 cross B3. So it's a four-dimensional handle body. And that's what you see in each of these three places, each of these three sectors. So same thing. This is called X1 sometimes. This is X2 and this is X3. And so they're all four-dimensional. And this is how we have divided trisected the 4 manifold into 3 pieces, each of which is a 4D handle body. So
Rob,
very much analogous to, well, there's 3 manifolds involved here. So if you take the red and the blue together, the red and the blue, the red union blue handle bodies is equal to a connect sum of K copies of S1, sorry, G copies of S1 cross S2.
Rob,
Yeah. That's
yeah, your 4-dimensional handle buddies and there's 3-dimensional handle buddies. Those are boundary connect sums.
No, it's. Oh yeah, they're boundary connect sums. Yeah,
Okay, fine. Thank you.
yeah. That's a boundary connect sum. Yes. So I used the wrong symbol. Right. And so then the boundary of this 4D handle body, K copies of S1 cross B3, is a. It's that. I said something wrong here. The red union of the blue, it's K. Yeah, it's K of those. So I said, I changed it to G and I shouldn't have. It's K, of course, that's what the boundary is. But what we're seeing here is the genus G, Haggard splitting of that 3 manifold, which is K copies. So that's the distinction between the K and the G. So that's what a trisection of a 4 manifold is. And in a sense, the best way to understand this is for me to give you a sketch of how it's created. All of this, by the way, is a joint work with Dave Gay and me. It's a paper in G&T about 5 years ago called Trisections of 4 Manifolds. So this is all joint work with Dave Gay, who was the leading figure in this. If anything, I was hanging on to his coattails. And so let me give you a sketch as to how this occurs, and you'll get a much better idea of understanding of this trisection.
Can I ask a silly question, Rob?
Sure, yeah, please.
Why 3? Why not 4 or 5 or?
Okay, so there's been generalizations to what are called multi-sections, and you see exactly this, except that you have a bunch of these sectors. Here you have 3 sectors, and you could have a bunch of them. Each one is a handle body. But what differs is that so you see here, any pair of these, like the red and the blue, or the blue and green, or the red and green, those are always connect sums of S1 cross S2s. But when you have more, you can take a splitting. Say if you have 4, just down here in the corner, you might have a multi-section with 4 things. Then this guy, any one of the 3, any right angle bit, that's a connect sum of S1 cross S2s. However, the splitting down the middle, that can be an arbitrary 3 manifold. And that allows you to do interesting things. They're still working this out. This is work of Gabe Islambouli, and he has a co-author whose name I forget, but Gabe Islambouli, Islambouli. And if you Google that, Gabriel, if you Google that, you'll find stuff. And that's for multi-sections. But that's, let me get back to, and please interrupt with questions, otherwise. So now how do we construct it? Well, we've got X4, and at the moment I want to take a Morse function from X4 onto the reals this onto the reals. So x4 is up here. And we have a Morse function going down to the reals, which I'm drawing horizontally, because I'm then going to take another Morse function, vertical. So this Morse function out of the reals has a critical point of index 0,
Rob,
index 4, yes.
I don't know if am
Oh.
I the only one who's
No, you
got,
lost it. Why did I lose it? What the
um,
heck? Why did that happen? Okay, it's back.
There you go.
I don't know why I lost it.
there you go.
I don't know why I lost it. Mysteries. So you have a critical point of index 0 and a critical point of index 4. This is a closed form manifold, so you only need one of each. And then you have critical points of index 1, some number of index 2, and some number of index 3. So now a neighborhood of this critical point of index 0 in the 4 manifold is just a bowl. You know, you take a neighborhood, it's going to look sort of like this. So I've just taken a neighborhood going out from 0 to, say, epsilon. And so above that, you see this bowl, which sort of in 2 dimensions looks like this. You see that bowl, but now I could take so at any level, say above epsilon, you see a 3 sphere. So this is a 3 sphere at that level. This is just a point, and this is a 4 ball because it's the neighborhood of the 0, the critical point of index 0, and then its boundary is a 3 sphere. Well, let's take a Morse function on that level set, and that Morse function, just say this is a vertical Morse function, so it has a critical point of index 3 up here, 2, 3, and an critical point of index 0 at the bottom, and no others. However, and so as you move, as epsilon approaches 0, you see other 3 spheres, and you see these critical points of index 3 or 0 all along there. And that's called a fold curve. This is called a fold curve. This curve that's projected onto the plane. It's called a fold curve. It's called a definite fold curve because this is like taking, if you imagine you've got a little cup paper cup that you put that holds your coffee, and you can take that cup and just fold it flat. That's the right picture here, where the cup is pointing to the right, and you just fold it flat.
Yeah.
So, okay, that's a definite fold. All right, so now you come to a critical point of index 1. And so what happens there? Well, this suddenly becomes S1 cross S2. That's what the 3 manifold becomes after you've gone past a critical point of index 1. So we've gone past that, and now you've got S1 cross S2, so take a vertical Morse function on it. Well, it has a critical point, still has a critical point of index 3 and 0, but now there's a pair of them in the middle, index 1 and index 2. And if you go back to the critical point, you'll see a picture like this. And now you have an indefinite fold curve. This is like a saddle point. Right there, it's like a saddle point. And so you have these, and now you have another fold curve, which is an indefinite fold curve, and you're just keeping track now of the Morse function. So as you go between the first critical point of index 1 and the second one, in between, you see this picture. And then you come to another one, and so then you see another one of these. Well, let's see, I got to expand this. So I'm going to expand this drastically up to here, drastically up to here, and this goes drastically up to there. I got to have room. And so I've just drawn 2 critical points of index 1. That's enough for our purposes. So you see this picture. Now you come to a critical point of index 2. And when you come to that, this critical point of index 2, that's index 2. And again, you'll see something like this. And now, what the 3 manifold is now, well, now, let's see, this critical point index, this will be, so going up, we could put a little arrow here, which is a 0. It's the same 0 as over here. And then you have an arrow here, which is a 1, because that was a 1 handle. Now you have something arrow here, which is 2, going up. And then this going up would be 1. And then this is still 2 and 2 and 3. Critical point index 3. Well, this is not, so now 2 features I want to emphasize here. First, we want this 2 handle, we want it to be attached to the level surface. So here we had a level surface, which is just a point, but here the level surface, well, there's a level surface here. With our 3 manifolds, it's the Haygarth surface. And that Haygarth surface at this point was a point, and now it's after you've added a 1 handle, it's a genus 1. Another 1 handle is genus 2. And now, so at this point in our picture, we have a level Haygarth surface, let's say, well, F of genus 2. And now I want this 2 handle to not just be somewhere in the 3 manifold, but I want it to lie in that surface. So if you have a surface, if you stabilize that surface, you can get this attaching circle of the 2 sphere. You can get that, of this 2 handle, you can get that attaching circle to lie in the surface if you stabilize the surface, if you increase its genus. So we do that by adding some cusps. So let's see, I'm going to erase this so I can add a cusp. So we add cusp. So a cusp looks like this. It's not round like before, but it's a cusp. And this is just like a birth in a Morse function. So this is a 1 handle, that's a 1, and that's a 2 going up. And this is the birth of a 1-2 pair. That increases the genus of the surface. And so now we've increased the genus enough so that this 2 handle is attached to that surface, to the Haygarth surface. And so okay. So we're going to do that with all the 2 handles. So there's more of them. However, there's a problem. We don't like having a Morse function with this critical point of index 2, this one, below this point of index 1. That's not a nice Morse function. But there's a trick we can do, which is called a swallowtail. So you can turn, let's see, let me draw it vertically. So if you have a curve, a fold curve like this, you can change it to, you can put in a swallowtail like that.
Rob, we can't see the bottom there.
Oh, I see. You can't. Well, I can see it, but you can't.
Yeah, could you just raise your picture a little bit? Or just draw it over a little bit? There you go. Thank you.
That's enough. Okay. Sorry. Thanks. Yeah, please enter. Yeah, so a swallowtail, when you do this, here's the picture I like. Imagine you got a loaf of bread. So this is a 1 parameter family of maxima as you go across the top of the loaf of the bread. So here's the loaf of bread. And it goes across like this. And here's the maximum at the top. So you have a one parameter family of maxima. And now you take, think of this as a loaf of bread. And now you take a dull knife and you start to slice diagonally. And when you slice, in the middle, it doesn't cut, but instead it turns this into that. You just put a dent in the top of the loaf. But because it's diagonal, this dent becomes over here, it becomes, well, I get it. That's higher than this is. Oops. And over here, it's lower on that side. And in the limit, this little bump here disappears. And over here, this little bump disappears and you just have the maximum. So what you see in this one parameter family, here's your original maximum. And then you have a birth, and now you have two maxima and a minimum. This is the minimum. And you continue across, and then you still have two maxima and a minimum, and then this pair die. That's this little guy here dying, and you're back to one maximum. So that's a move in singularity theory, where you can put in what's called a swallowtail. So I want to do that. And so to avoid going to a new screen, I'm just going to erase this guy right here and replace it with a swallowtail. So it goes down like this, and back like that. And now, okay, we replaced it, and now what we can do with this, that's useful is that we can, in a Morse function, you can always lift a critical point of index 2 above a critical point of index 1. That's just transversality of descending and ascending manifolds. So I'm going to lift that above. And so I'm going to erase this. And then what we see now is just this. Geez, I'm terrible. I'm having a terrible time drawing here. So I want to see this swallowtail, which I am screwing up. I want it to go there's this. Only now this, I took this line and I lifted it above that line. So that's not the picture I want. I really want just yeah, this is what I want. I want this picture. That's what happens. That's what happens when you down here, if you take this curve, this arm, and just bend it over that way, and you take this arm and you bend it over that way. You're just bending. And this is what up in our picture, it just means that you are lifting a critical point of index 2 above a critical point of index 1 in our vertical Morse function. Okay, now ask questions. Please interrupt if this is not clear. So we do this with all the critical points of index 2. So we have some more pictures like this. And so now we're out to here. We're out to this spot, and we haven't done the critical points of index 3 yet. Shortly, you're going to see the punchline. Now, the critical point of index 4 is, again, lies over here. And again, you get a thing that looks like this, just like the outer circle on the left side. And then you have some critical points of index 1, and those are just one handles. So they look like this. And there's a bunch of them. And then you arrive at this level. Well, sorry, this really goes down to right in there, because all the three handles we've taken care of, because they look like one handles from the other side. So now this manifold right here is what? It's a connected sum of S1 cross S2s. It's a Morse function on that. And here you have another Morse function on the same manifold. So surf theory says these can be connected by a surf diagram. So that may involve more stabilizing on this side. So you may have to stabilize with some cusps like we did before. That's just a canceling 2-3 pair. So there may be some of those. There may be more of those. We may need more of those on this side. So let's put in a few more. Let's put in a few more of those. They can go anywhere. And then the 3 handle goes across, the 0 goes across, and then all the rest, there's a surf diagram where the 2s match up in various ways. Well, there wasn't enough of those. We need a couple more of these guys. And then they match up here in various crossings like that. So this is what you do just with Morse theory, the horizontal Morse function, then the vertical Morse function, and some surf theory. This is all Morse theory and surf theory so far. And now the key to this is, well, because we've stabilized a lot, we have a surface, our Heegard surface has started out as just the 2-sphere, but it's gone all the way up to genus G. So here we have a map now of our 4 manifold down by the 2 Morse functions onto the plane. And over this is a surface. And now I want to draw 3 arcs. So I'm going to draw from here. The key thing is to draw, let's see, which way do I want to do it? I guess I want to draw a red arc out to the boundary. And then I want to draw a blue arc out this way to the boundary. And then I'm going to draw a green arc, and it's just going to go this way. And now that's topologically, this is a disk on the outside where the outside circle is. And there's our 3 arcs. And now what's inside? Well, the key feature of this, the key feature is that inside each wedge, each of these 3 sectors, so between the red and the blue, you'll see that each arc, either like this arc, this one right here, why is that blue? That arc has no cusps on it. This arc has got 1 cusp on it, namely this point. And this one, that arc between the red and the blue just has 1 cusp. And it's having at most 1 cusp that is the crucial thing. And now if you look between the red and the green, this arc has got 1 cusp because there's no more cusps on it. In fact, the only cusps in here are the ones that are coming from these guys. There's no other cusps. And otherwise they're just curves. And then the same thing up here. Every arc up here Either it has no cusps, like that one, or it has a cusp that looks like, well, this could have come down to here. And then that arc between the red and the green has only one cusp. That's what makes these three sectors equal to, so this is a connexum of K S1 cross B3s, where K is the number of these curves with no cusp. So K is the number with curves with no cusp. And then the rest of them do have a cusp, these cusps, and that brings you up to G. So this is, so now there's a few things to check. Y is, for particular the cusps. Well, what is a cusp? A cusp is, it arose as a birth. In Morse theory, it's just a birth. And if you have a Morse function, you put a birth in, that doesn't change the topology. So the cusps don't change the topology. So the one handles that you see in these curves that don't have a cusp, that's an actual one handle, and that gives you an S1 cross B3.
Rob?
Each time you, right, something's
Yeah,
happening.
Rob,
Yeah.
why is
Why?
a cusp not critical cancellation?
It is. It is,
Yeah,
and
yeah,
that's
you said
why
it was
it's a birth. It's a birth, which is a cancellation. And so that doesn't change the topology. If you take a Morse function on, so in this case, if you're looking at our vertical Morse function and I draw this cusp more like this, if you're looking at a Morse function on that vertical three manifold, then putting in that cusp doesn't change the topology. It just changes its Hayguard splitting, but it doesn't change that three manifold. And so going past a cusp doesn't change the topology. And that's why it doesn't increase the number of S1 cross B3s.
Yeah. Rob, isn't it just the stabilization of the Hayguard splitting?
Yes, yes, yes,
Thanks.
that's exactly it. So that's why, so the crucial thing in getting a trisection was seeing this picture. When this picture had come to Dave Gay and I earlier when we were looking at just maps of the Morse 2 functions from a four manifold of the plane. And then turning that into a trisection meant the observation that you could draw the red, blue, and green curve lines so that there's only one cusp on each. As I said, only one cusp as you go from here to here. And so there's a proof that trisections, you have to check details, but that's the proof that a four manifold has a trisection. And you understand a lot more from it because not only do you just have these red curves. So what do you see on sigma G? You see G, you see a cut system. You see G curves that you fill in order to get that handle body that lies over the red arc. And you see a different cut system, a different collection of G curves that give you the blue handle body, and then a third collection of green curves that give you the another handle body. Right. So with that under your belt, you can describe the four manifold by the three cut systems. You don't need all these fold curves. You don't need all of those. You just need the fact that you start with the surface and you cross it with a disk. So that's what you have over this center disk here. It's just the surface cross a disk. And then as you go out to red, you add two handles to those red circles and you fatten them up. And so then you've added a bunch of two handles and a three handle to to the surface across the disk. And you do the add the red two handles, you add the blue two handles, you add the green two handles. And now you have a four manifold with boundary. And because the red together with the blue is a connect sum of S1 cross S2s, you're just going to fill that in, and there's no interesting way to fill it in. I mean, there's only really one way to fill it in by an old theorem of Pointeroo and who's his co-author? He's the guy who proved theorems about embedding two spheres in three manifolds. Can't think of his name. Forget names these days. Anyway, it's a theorem of Pointeroo that there's no exotic way to add in the S1 cross B3s. So that means you've got your four manifold, and it's given to you by the Heegard surface and the three sets of cut systems. So that's a trisection of a four manifold. Now, okay, now I don't want to lose all that, because I want to move over to group trisections. So so as not to squeeze things too much, I will erase this part. And you have this picture of the group trisection of the trisection of the four manifold. So now apply the pi1 functor. So what does that mean? Well, what's pi1 of the central surface, the surface sigma g that lies over that central point? I'm going to describe a cube of groups and epimorphisms. So we're going to start at one corner with pi1 of S3, so the surface group, pi1 of
Have we lost Rob?
Yep.
Can you hear me, Rob?
Seems to have quit drawing too.
No.
He's not moving on the screen.
Oh, it's frozen.
Where'd he go?
I wonder if he's got one of those Zoom contracts which deletes itself after 40 minutes.
Ah,
It's going to be dependent on your contract.
He'll be back when he realizes he's not.
call him or email him or something.
I'm going to invite him again. I'll send him an email.
If the boss is facing the blackboard and not looking out in the room, then she might not notice that the room has been cleared.
He's not on the participant list either.
Oh. Well, I've sent him an invite anyway. So if he looks at his emails, he might be able to get back in. Isn't technology wonderful?
Is anyone else prepared to give a talk?
Anybody got
You
a?
extracted 45 minutes out of Rob. That's actually pretty good.
It started to get good.
Maybe the internet bosses didn't approve of what he was saying.
No, it's been
Yeah.
censored.
That's right.
Yeah. Well, what can I say? This is the last talk this term. That's something.
Maybe we can get Rob to come back and finish the talk at the beginning of our.
That's a
Rec-
great idea, Lou. Let's do that. Yeah.
You may want to stop recording, Roger.
Well, okay. I'll stop recording. I'll pause it.